Join our exploration journey to the closest celestial body, the Moon. We'll investigate its physical characteristics and orbital motion. Learn more about the lunar phases and eclipses and understand the relation between ocean tides and moonquakes. Find out how and when our natural satellite was created and what is the process that shaped its surface. Explore the alien landscape covered with craters and ancient seas of lava. Witness the extraordinary achievements of the historical missions and discover which is the precious resource that is fueling the new space race to the Moon. Sit back, relax, and enjoy the show. The Moon, the closest celestial body to our planet and its sole natural satellite. Since the dawn of human civilization, it has been one of the most significant objects in the sky, alongside the Sun. The Moon is the fifth largest satellite in the solar system and the largest compared to the planet it orbits. It exceeds the size of all the dwarf planets in our system, and its mass is equivalent to that of a small planet. The diameter of the Moon is approximately 1/4 of Earth's diameter. Our satellite orbits at a distance of roughly 380,000 kilometers. As a result of the strong gravitational interaction between the two bodies, the axial rotation of the Moon is synchronous with its orbital motion. Therefore, we constantly observe only one of its sides. The Moon completes one orbit in just about 27 days, and the period between two identical phases is around 29.5 days. In the distant past, lunar phases served as a measure of time, and it is no surprise that the words month and moon share the same linguistic root. The orbital phases of the Moon depend on its position relative to the Sun. We distinguish four major lunar phases. When the Moon lies between the Earth and the Sun, its visible side is entirely unlit. The lunar disk is not visible, so we call this phase a new moon. Over the next week, the lunar disk gradually begins to reveal itself as a crescent, bulging out towards the setting sun. By the end of the second week, we already see half of the lunar disk, and we call this phase the first quarter. Approximately 1 week later, the Earth stands between the Moon and the Sun, and then we see the lunar disk fully illuminated. This phase is called a full moon or a second quarter. During the following week, the disk of the Moon decreases, and by the end of the seventh day, only half of it is visible again. That marks the third quarter of its phase, also known as the last quarter. From here on, the illuminated disk keeps decreasing and takes the shape of a crescent, bulging toward the sunrise. Interestingly, when the lunar disk appears as a crescent, the non-illuminated part is also visible, although barely noticeable. That is due to the sunlight being reflected and scattered by our planet. The size of the lunar disk seemingly matches the apparent size of the solar disk, although the diameter of the Moon is about 400 times smaller. That coincidence is due to the distance between the Earth and the Sun, which is about 400 times greater than the distance to the Moon. Therefore, when the Sun, Moon, and Earth line up, we can observe a total lunar or a total solar eclipse. During a total lunar eclipse, the Moon does not disappear. Instead, it looks like a faintly glowing red-brown disk. That is again due to the light reflected by our planet and the characteristics of Earth's atmosphere. Oxygen and nitrogen molecules scatter blue light, which is why the sky on Earth appears blue. Mostly reddish light reaches the Moon, being the reason for the particular color of its disk during a total lunar eclipse. When the Moon is positioned between the Earth and the Sun but does not obscure the solar disk completely, we observe a partial solar eclipse. Similarly, if the Earth stands between the Sun and the Moon, but its shadow does not cover the totality of the lunar surface, we observe a partial lunar eclipse. Total solar and lunar eclipses do not occur at every new or full moon because the lunar orbit is an ellipse, with an inclination of about 5 degrees relative to Earth's orbit around the Sun. The cycle of eclipses repeats approximately every 18 years, and this period is called a Saros. An average of 42 solar and 28 lunar eclipses occur within one Saros. The proximity of the lunar orbit to Earth has a significant impact on our planet. As a result of the Moon's gravitational force, we observe 2 high tides and 2 low tides in Earth's oceans every day. Tidal waves form in the direction of our satellite and on the opposite side of the planet, moving from east to west. The Earth has a similar gravitational effect on the Moon, which creates tension in the lunar mantle, leading to moonquakes. There is a general misconception that the Moon revolves around the Earth's center of gravity. In fact, the two bodies move as a binary system, orbiting a common center of mass called a barycenter. It is located about 4,700 kilometers from the center of our planet in the direction of the Moon. The barycenter moves in an elliptical orbit around the Sun, and the Earth and the Moon complete one revolution around it in approximately 27 days. Over time, our satellite is moving away from the planet, increasing the distance by 3.8 centimeters per year. That is due to the gravitational interaction between the two bodies, which slows the Earth's axial rotation and increases the orbital period of the Moon. The change in Earth's rotational period is negligible and leads to an increase in the length of a day by 17 microseconds each year. The gradual receding of the Moon implies that eons ago, it was much closer to Earth. Unfortunately, there is insufficient data on when and how our satellite formed. The prevailing theory suggests a collision between early Earth and another protoplanetary body. Computer simulations have shown that an impact with a small planet with a metallic core could have ejected enough debris from Earth's crust and mantle into orbit to form the Moon. Studied isotopes from the lunar surface indicate that this event likely occurred no later than 100 million years after the formation of the solar system. The hypothetical protoplanet is named Theia, and its core probably was absorbed by the heavier core of the Earth. That theory is supported by the similarity between the average density of the Moon and the density of Earth's mantle, as well as by the low concentration of heavy elements in samples from the lunar surface. After the collision, both Earth and the newly formed Moon were entirely covered by oceans of lava. At that time, the Moon was much closer to our planet. The high temperature of the molten Earth vaporized some of the nearby lunar crust, which later condensed on the opposite, more rapidly cooling side of the Moon. That explains the presence of a thicker lunar crust on its far side. A few hundred million years after the formation of the Moon, the solar system experienced a period of so-called late heavy bombardment by comets and asteroids. The migration of the outer planets directed millions of smaller bodies toward the interior of our system and triggered intense collisions. The impacting objects formed huge craters on the lunar surface, later filled with lava from volcanic activity and solidified. Thus were formed the dark regions of the surface historically called lunar maria, meaning seas in Latin. Those are lower and relatively flat areas, mostly found on the visible side of the Moon. The thick crust on the opposite side has prevented the formation of deep craters, so the maria are less common there. Lunar craters range from a few centimeters to hundreds of kilometers across. The largest crater in the entire solar system is located on the far side of the Moon near the South Pole and has a diameter of 2,500 kilometers and a depth of 13 kilometers. The The bright areas on the lunar surface are called terrae, meaning continents, because they have higher altitudes and more rugged terrain. The highlands are significantly older than the maria, hence, they contain more craters. Some of the larger ones exhibit bright radial rays, which are the byproduct of ejected material during the impact event. A thin layer of dark gray dust covers the lunar surface. Beneath it lies the lunar regolith, a loose non-homogeneous material, constantly eroded by cosmic radiation and meteor impacts. The lunar crust has a depth of about 70 kilometers on the visible side and reaches up to 150 kilometers on the far side. It contains silicon, magnesium, oxygen, iron, calcium, and aluminum. Although seismically active, the moon does not have tectonic plates, and there has been no volcanic activity for millions of years. The gravitational force on the moon is approximately 1/6 that of Earth's. Weak gravity and the lack of a magnetic field prevent the retention of an atmosphere, so our satellite has only a very thin and rarefied exosphere. The absence of atmospheric pressure excludes the presence of liquid water since water molecules pass directly from a solid to a gas when heated. Without water and an atmosphere, erosion processes similar to those on Earth could not occur. That is why the lunar surface has remained unchanged for billions of years. Over the course of a day, the surface of the moon experiences drastic temperature fluctuations. During the lunar day, which lasts about 2 Earth weeks, the temperature reaches almost 130 degrees Celsius, and during the lunar night, it plummets to around -170 degrees Celsius. Radiation from solar wind and cosmic rays renders the moon even more inhospitable. The background radiation is about 200 times higher than on Earth's surface. Under such conditions, it is not surprising that the moon does not support any living organisms. Despite its hostile environment, the moon remains a subject of scientific interest for humanity, and research continues to this day. The earliest observations of the moon with a telescope, made by Galileo Galilei, date back to the early 17th century. During the previous decade, we confirmed the presence of significant amounts of water ice on the lunar surface. They exist in permanently shadowed craters around the lunar poles, especially the South Pole. Water is one of the most valuable resources in space. Harnessing those water reserves would allow the creation of habitable lunar bases in their vicinity, and the creation of favorable conditions for the emergence of life. The confines of its home. The future of mankind and the beginning of the long journey to more distant worlds starts with the moon, the nearest island in the vast cosmos.